Next speaker, Dr. Vishnu S. Pendyala Garu. Dr. Vishnu S. Pendyala is a faculty member of Department of Applied Data Science at San Jose State University and is the chair of the IEEE Computer Society Silicon Valley chapter. He has over 2 decades of experience in the software industry and delivered several invited talks during his 3-year term as an ACM distinguished speaker. He holds MBA in finance and PhD, MS, and BE degrees in computer engineering from US and Indian universities. Dr. Pendyala taught a 1-week course sponsored by the Ministry of Human Resource Development, MHRD, Government of India, under the Gyan program in 2017 to computer science faculty from all over the country and delivered the keynote in a similar program sponsored by AICTE, Government of India, in 2022. I request sir to continue with his session. Thank you.
Thank you for the kind introduction. Let me set up my laptop. 1 second. System settings. I think there is some flakiness in the. What's in that? Okay.
Duplicate to
Slideshow. Presenter view. Okay. What's in here?
object. A light object.
Oh, screen share, yeah. There is flakiness. There is a loose contact on it.
The screen share sessions. Now screen shares.
Okay, so the next thing is to share the screen. Share.
Mute system. Okay. Right.
Mute video off, right?
Right.
Okay, good morning, everyone. So I'll be talking about deep learning, particularly deep learning similarities. That is to learn similarities in data. I'll talk about a few techniques, applications, and future directions. So hopefully you'll be able to follow through. I made it quite easy for you all to follow. So don't be apprehended or inhibited when you look at the title. So if there is one word to characterize all of machine learning, including deep learning, that one word would be similarity. I don't know how many of you are students of machine learning, but if you have studied a little bit of machine learning, you would recognize that dot product is ubiquitously used in machine learning, right? The vector dot product. So what is the semantics for dot product? What does the dot product of two vectors mean? It conveys the similarity between the two vectors. right? And dot product is ubiquitously used in machine learning and deep learning. So, so similarity is very inherent to machine learning and deep learning. We can accomplish substantial tasks using this concept of similarity by discovering similarities and dissimilarities using deep learning. So let us take some examples, right? So how does Netflix recommend movies? Or how does Google translate from one language to another? You would have used all these applications several times, right? Google Translate helps you translate from one language to the other. How does it do that? iPhone recognizes faces, right? You open an iPhone using the face recognition technology. And banks typically detect fraudulent transactions. How do they do that? And how does Yelp classify uploaded photos? You upload a photo of a samosa you ate in a restaurant, it immediately recognizes it as a samosa. How does it do that? So it is all based on similarity of features, right? So a person liking one kind of movie is likely to watch similar movies, right? Similarly, a language translation that Google accomplishes is essentially finding similar words. So in English, how are you? In Telugu, ela unnaru, right? Similar words. And facial recognition is all about detecting similarities in the features of the new face with those saved earlier, right? And fraudulent transactions are similar. There are certain features in the fraudulent transactions which indicate similarity. That's how the banks detect fraudulent transactions. And Yelp uses also similarities between photos, right? A new image of a samosa is likely to look like the old images of samosas. So all these applications basically use similarity in one way or the other. Another question, how does Netflix know that these movies are similar? So these are all movies, I'm pretty sure you would have watched quite a few of these movies. So how does Netflix know that these movies are similar? Ben-Hur, Last Emperor, PS1, Gladiator, Bahubali. So Netflix, which uses some kind of machine learning algorithm, works by discovering similarity of features of various movies, right? In general, machine learning algorithms work by discovering similarities among the features. The more powerful algorithms discover latent features. Latent means hidden features. See, the features for these movies are not explicitly given, right? You just have some features which are not explicit, which do not explicitly indicate that there is a genre which is common across all these movies, a theme that is common across all these movies. So there's a latent feature which is common across all these features, all these movies, right? And that latent feature is probably the machoism, dynasty, monarchy, battles. These are all the common theme across all these movies. So these features which are hidden have to be discovered. How do we discover hidden things? You take a simple example of light. Light is white. How do you discover what's inside the light, white light? You pass it through a prism and you get the spectrum out of it. You get the 7 colors in the white light, right? So similar kind of methods exist in machine learning also, in mathematics. These are called spectral methods. A very simple and commonly used spectral method, which you all know, is, which you all studied in probably high school or 11th grade or 12th grade, is the eigenvalue decomposition, right? Eigenvalues essentially bring out the latent features of a matrix. So that is one such spectral method. So using such spectral methods, you can bring out latent features of data. Data in this case is the movies, right? So latent features is crucial. So we can define machine learning, the various tasks done in machine learning, all using similarity, right? So some of the common tasks accomplished by machine learning are given here. One is classification. So what is classification? In terms of similarity, it is basically determining how similar a new object is to the objects already known to belong to one or more classes, right? You basically find the similarity. The other task that is done, that is accomplished using machine learning, is regression. So in this case also, identifying a place for the new object among several other objects arranged according to similarities. Right? Here also similarity plays a big role. And the third kind is dealing with sequential data, or the time series prediction, which we'll talk about in this talk a little more in detail. So in time series prediction, we assume that the data follows a pattern, and then we predict a new data item that similarly follows the same pattern, right? There are other tasks accomplished by machine learning, deep learning. One of the most important tasks is generative modeling, right? You would have heard about this website called, what is it called? thispersondoesnotexist.com. Did anyone visit that website? Thispersondoesnotexist.com. I can show you an example. This person does not exist. Oh, I have to share this, right? Oh, I'm not able to share it. Okay, that's okay. I'm not able to share it for whatever reasons. That's okay. But you can always check. This person does not exist. It generates real looking people's faces out of nothing, out of noise, basically. So that again is also based on similarities. You generate similar objects. The model is fed some data, and the model generates data which is quite similar to the data that it is fed on. So almost everything that you can do with machine learning has some amount of similarity. But let us start simple. So data has features, right? Machine learning is all about features. You all know that. So features are often vectorized. There are different ways to deal with features, but typically the way to deal with features is vectors, as vectors. How is their similarity computed? How do you know that two vectors are similar? By using what is called as a dot product, which results in a scalar number. So dot product, like I mentioned earlier, it's ubiquitously used in machine learning. So machine learning is all about computing similarities. It's all about computing dot products, and dot products essentially mean similarities. So it's all about computing similarities. And another analogy is human learning, right? Machine learning is similar to human learning. So human learning is mostly based on similarities, right? How does a good teacher teach you new concepts? Suppose you have taken a very complicated course. How did you understand the new technology? By comparing it something with that you already know, right? You compare it with something that is similar, right? That is how the intuition is explained. So even human learning is heavily based on similarity. So some of the algorithms, if you have studied machine learning, algorithms like k-nearest neighbors, support vector machines, kernel machines, these are all algorithms which use the concept of similarity directly. And in general, dot product of vectors represent the semantics of similarity. And matrix multiplications are essentially a series of dot products. What do you do in a matrix multiplication? You just do several dot products, right? So, and dot product is about similarity. So, and machine learning has a lot of matrix multiplications. So you can, in that sense, you can think of machine learning as determining similarities. It has been recently proved that any algorithm that uses Gradient descent. Gradient descent is a workhorse of machine learning. It's the main tool used in machine learning. And it has been proven recently that any algorithm that uses gradient descent is essentially a kernel machine. And kernel functions are basically measures for similarity, right? So that means there is formal proof that deep learning and machine learning, which use gradient descent, have to do with similarities. So there's a lot of connection between machine learning and similarity. So we exploited this connection between similarity and machine learning and deep learning particularly to do some experiments to accomplish significant things. So the first topic I'd like to talk about, first research work that I would like to talk about is to build a music tutor using two deep learning frameworks called LSTM and CNN. The second is to convert melodic frameworks, right? What is a melodic framework? Does anyone know? Melodic framework is a fancy English word for what is typically known in Indian languages as raga. You all know ragam, tanam, pallavi, right? So raga is basically called melodic framework. So, so the second research problem that I wanted to give some insights about is melodic framework conversion using CycleGAN. So we used a framework called CycleGAN to convert South Indian ragas, Carnatic music, to Hindustani music and vice versa. And the third application I would like to talk about is transcoding. That means converting programs in one language to other. So particularly between Python and R is what we did. We did some experiments to convert programs in Python to R using, again, the concept of similarity in deep learning. So first is learning music similarities. So I know most of you are probably ECE or electrical engineering students, but I would still, in case you're not very familiar with analog signals and audio signals, I just wanted to give a brief introduction to music, the math behind music. So music, we all know from elementary school, is made of waves, right? So the simplest music is a sine wave, right? And the sine wave, the sound from a sine wave is basically like a tuning fork. You just hit a tuning fork, and the sound that it makes, the waves it forms, is like a sine wave. That's the simplest music. So how many frequencies are there in this sine wave you are seeing on the screen? There's just one frequency, right? The repeating pattern, there's only one repeating pattern. And what is the frequency? You divide 1 by the period, you get the frequency, which is 1 by 0.2. The period is 0.2. It is repeating every 0.2 seconds. So the frequency is 5. So the good thing is all these are numbers. The frequency is a number, the amplitude is a number, the period is a number, all these are numbers. So that means we can do some math with it, mathematics. And deep learning is applied math, right? So here's an example of a slightly more complex sound wave. So how many repeating patterns are there in this sine wave, in this wave? There are 2 different repeating patterns. So that means there are 2 frequencies. In fact, this wave you are seeing on the screen is the sum of 2 different sine waves of different frequencies. You just add them up, you get this sine wave, right? So there are 2 frequencies. So as you can see, the sine wave on the left-hand side is basically a sum of the sine waves on the right-hand side. So you can visually add the amplitudes of the 2 sine waves on the right-hand side to get the wave on the left-hand side. And if you look at the code below, the periodical wave is a literal arithmetic sum of the 2 sine waves on the right. So it's a literal arithmetic sum. So it is that simple. Now, Here are a few waves produced by a guitar string. When you pluck a guitar string, that's the wave produced. And if you hit a cymbal disc, you get this kind of a this kind of a wave. So as you can see, again, there are many frequencies, many sine waves. You add up many sine waves to get this sine wave. So how many frequencies are there? Does anyone know how to know the answer? So in general, every periodical sound wave is made of one or more sine waves. So the wave on the left-hand side is composed of several sine waves on the right-hand side, right? So how do we extract the frequencies from these complicated sine waves, these complicated waves? So frequencies are essentially the latent features of music, right? We talked about latent features like Bahubali and what is the other one? PS1. There are some latent features, right? How do we extract the latent features? From music, the frequencies are the hidden features. So again, we need some kind of a spectral method. We have to pass it through a prism which lets out the hidden features to discover these latent features. And the prism that we use in mathematics is what is called as a Fourier transform, right? So you pass the amplitude as an argument to the fast Fourier transform method, and you get the frequencies. So in this case, there's only one frequency in the sine wave on the left. So there's only one frequency that is output by the fast Fourier transform. I mean, fast Fourier transform is a discrete form of Fourier transform. The complexity is greatly reduced. Fourier transform has a complexity of O(n) square, which is really expensive. The fast Fourier transform has a complexity of n log n. So it's very efficient. So we use FFTs to generate the frequencies. So now in the left-hand side wave, there are two frequencies. And again, we use the FFT to generate the two frequencies. So that's a little bit of introduction to the music, the math behind the music. Now let us look at the applications. So melodic framework, also called as rag in North India and raga in India probably, is unique to Indian music. Indian classical music is unique in its requirement for very rigorous training, right? So I attempted to learn Carnatic music when I was a student, like most of you in this room. But I was denied for various reasons. And one of the things that put me off is because it takes typically 10 years, at least 10 years of rigorous training to start singing Carnatic kirtanas, right? So it is a very rigorous process. So that frustration led me to this application. So I thought, why not use deep learning to come up with a music tutor? The reason being, music is a series of raga, particularly the Indian music, which conforms to certain ragas, certain raga, is a time series of swaras, right? There are a lot of notes, and it's a time series of these notes, right? And then we talked about time series, the similarities between time series and all that stuff, right, in deep learning. So it should be pretty straightforward to detect the time series conforming to a melodic framework. So each melodic framework, you all know, evokes a different mood and inspires different feelings. And there are stories abound about how music has cured diseases, it has cured a lot of things, right? So the raga is a very powerful concept in Indian music. And fortunately, the raga is very amenable to deep learning. So that is what we took advantage in this project, me and my students. So the first project is to build a music tutor. And in that process, the first step is to identify the raga from an audio signal. So how do you identify the melodic framework in an audio signal? So for that, we used sight. So from sound, we now move on to sight. We convert music to an image. How do we do that? We use what is called a spectrogram. So this is a spectrogram for this music. Oh, 1 second. So when you play this one. So when you play this, this is a music snippet. You would have all recognized that music, right? It's from a movie, famous movie by Ilayaraja. I mean, the music is by Ilayaraja. So that music clip can be represented using this image. This image is called a spectrogram. In fact, a spectrogram can be reverse engineered to produce the sound that you just heard. This spectrogram can be reverse engineered. So we can think of the spectrogram as a graph of energy in a signal as a function of time and frequency. So the fine changes in the color across the time and frequency domains captured in the spectrogram give substantial insights into the music clip, right? In fact, some experts can even recognize spoken words from a spectrogram of speech spectrogram. So what is the advantage of converting music snippet to image? The advantage is that you can now treat the problem of identifying the raga as a problem of image classification, right? You classify the image as belonging to one raga or the other, and that's it, your problem is solved. Now you have converted audio processing problem to an image processing problem, right? So that's the idea behind this project. So, so how do you, the code for generating a spectrogram is pretty straightforward. It's given on the right-hand side. So how many dimensions are there in the spectrogram? You can see only 2 dimensions, but actually there are 3 dimensions. X-axis, Y-axis, and the third dimension is a color, right? So the X-axis is time, Y-axis is frequency, and the third dimension, which is the color, represents the amplitude. So, and we all know how to find the frequencies, right? How do you find the frequencies? We use Fourier transform. So we use Fourier transform to find the frequencies, plot them across time, and color the plot based on the amplitude. That's how you generate the spectrogram. And the code for that is pretty straightforward. Just a few lines, 2 or 3 lines of code to generate the spectrogram. This is the spectrogram for a song in Rag Bhairavi, right? This is a North Indian raga, Bhairavi. You can also generate chromograms. Chromograms are a little more robust. It's basically like a spectrogram, but it's a little more robust. So I will not spend a whole lot of time. And the other way to process sound waves or music is by what is known as MFCCs, Mel Frequency Septral Coefficient. Septral is obtained from spectral, right? You all know spectral. Just rearrange the letters in the word, you get septral. So MFCCs basically model the way human hearing works, right? So if you have noticed, our ears are better at discerning resolutions at lower frequencies. You are able to make out words spoken at lower frequencies and large, loud frequencies, right? So that is what MFCCs do. They basically convert the frequencies to a log scale. And you know what log does, right? Log de-emphasizes big numbers and emphasizes small numbers. That's the function of log. So that is what MFCCs accomplish. So the MFCCs basically align with the human perception of audio. So this is the other way of processing an audio signal. Now coming to the deep learning. I'm not sure how many of you are familiar with the LSTM framework used in deep learning. In 20th century, for time series data, LSTM was the most widely used framework. Long short-term memory. It stands for long short-term memory. So it has been used for time series. Music is basically time series, right? You have a bunch of frequencies measured across the time scale. So it's a time series. Anything measured across time is a time series. So LSTM is basically a special kind of recurrent neural network. The model consists of a memory state, which helps to remember or forget features like how music comprehension works in human beings. So how do you recognize ragas? The last 7 swaras or whatever number of swaras play a big role in determining the raga, right? So you observe the time series, the swaras across the time, and then that's how you recognize the raga. And the thing is, you don't typically pay attention to the entire song to determine the raga, right? Some of the swaras, some of the sounds are not all that important, some of the swaras are important and things like that. So these dependencies between the swaras and the notes in the music are captured using this kind of a framework. So each one of these is a neural network. These boxes is a neural network, right? And neural networks basically work by adjusting the weights, right? So the weights are adjusted so that this box learns to recognize what swaras are important to recognize the raga and what portions are unimportant to in terms of recognizing the raga. Sorry, is there something you are trying to tell me? Okay, not for me. Okay. So so that's the framework. The framework, and I don't want to go into too many details for lack of time. The essential idea is to capture dependencies in a time series. That's what it does. Another example is like reading newspaper, right? Typically, any experienced reader would not spend more than 5 to 10 minutes reading a printed newspaper, right? How does he accomplish that? By looking at the important words, he or she is able to gather the essence of the news article, right? So some of the words are ignored, some of the words are given importance. So how does a human being know which words are important and which words are not important? Based on training. He would have read newspapers several times in his life, he or she, and he would recognize which words are important, which words are unimportant. So that's what happens in this box. This box recognizes which dependencies are important and which dependencies are not important. So that's the idea behind LSTM. And then there's a little bit of math. This math need not scare you, actually. This is a very simple math. The sigma stands for what is called as a sigmoid function. Sigmoid function is any function in the shape of S. If you plot that function, it is in the shape of S. So these are all simple math operations. The two very common sigmoid functions are used in machine learning are logistic function and the tanh function. Both are used here. So using this simple mathematics of mathematics and a little bit of algebra, you are able to do substantial things with the data given to us. So we need to come up with a topology for the neural network architecture, the deep learning framework. So this is the architecture used. In case if you are using MFCCs, if it is spectrogram, then it is straightforward. You use image processing. The framework used for image processing is typically CNN, a convolutional neural network. I will not go into the details of that. But so if it is spectrogram, we use CNN, and if it is MFCCs and things like that, we use LSTM to classify the given music snippet into one of the ragas on which it is trained, right? So once the system learns to recognize ragas, melodic frameworks in the music, so it is just a matter of the music learner uploading his practice, his or her practice, to the cloud, and the cloud basically sends back some feedback, whether the practice conforms to the raga or not, and then some guidance as to what, how it can be improved. So that is the idea behind the music tutor idea project. So the next project I wanted to talk about is to convert ragas from one North Indian style to South Indian style and vice versa, right? So for that we used what is called as a cycle GAN. So the original framework of a cycle GAN was proposed for converting images, similar looking images. So in this case, the original paper talked about converting images of horses to images of zebras. So to accomplish this, you would need lots and lots of data, lots and lots of images of horses and corresponding images of zebras, which is very difficult to obtain, right? So how can you obtain an image of a horse? Like, I mean, getting an image of horse is very easy, but how do you obtain an image of a zebra which is standing in the same position and everything is same? That is very difficult, right? So that is the reason why they came up with this idea of cycle GAN. GAN stands for Generative Adversarial Network. I will not go into the details. I have some videos on my YouTube channel and IEEE.tv as well. You can look at them to get more insights. But the idea is that you'll be able to generate similar looking images for different entities. So that is the idea. So this is the schematic for our research project. So the cycle GAN essentially has a pair of generator and discriminator. The generator and discriminator constitute a generative adversarial network. So the first pair is pink, and the second generator discriminator pair is in green, right? So the first pair, the pink boxes, work to convert music in a North Indian raga called Bhairavi to a South Indian raga called Shanmukha Priya, and the second pair does the reverse of it, vice versa. So the generator discriminator pair works just like in a generative adversarial network. Just like the fake images are generated using GANs, similarly, they work in conjunction with each other to generate music in this case. But the only difference is in the fake image generation, you start with noise, whereas in music, you start with these original samples. So the original samples of Bhairavi and Shanmukha Priya are in yellow. And so these generator discriminator pairs do the conversion using a loss. Machine learning basically works by computing what is called as a loss, right? So in this case, the loss computed is a cycle consistency loss. So the Bhairavi raga music snippets are converted to Shanmukha Priya, and then they are passed to the second pair of discriminator generator to convert back to Bhairavi, and then a cycle consistency loss is computed, and the goal is to minimize the cycle consistency loss, right? So the weights are adjusted in such a way that the cycle consistency loss is minimized. So that is essentially the concept in the philosophy behind converting from one raga to the other. Now, the third and the last application I wanted to talk about is transcoding. So this again is a conversion, but we use a different kind of approach to do this conversion, right? And so it's a different kind of conversion, and it's a different way to convert also. So again, we cannot obtain parallel corpus of programming language, right? So given a Python program, finding identical, in this case, C++ program is a challenge, right? So, so we use some NLP techniques, self-supervised learning techniques, to do the conversion. So Facebook has a solution, but the solution is a bit limited. So we, and then it doesn't apply to many languages. So we used similar techniques to convert from Python to R and vice versa. So the idea is basically to map the keywords in the programming languages to a latent space, a hidden space. So discover the hidden space of programming languages and then map the keywords to programming languages. Like in this case, you can clearly see that Boolean, bool and char are quite similar. And what else is there? Catch and except is also, so in one language it is called catch and in the other language it's except. So they are all plotted together. In the latent space, they appear together, they're nearby. So there's a latent embedding space. These kind of techniques are used in your ChatGPT also. If you have tried ChatGPT, these NLP techniques are used there also. So the idea is basically to map Python code and R code to a shared embedding space. And then from there, from the shared embedding space, once you have something like this, now in one language it is str and in the other language it is string, right? So it is just it is just mapping this word to this, which is anyway very evident from the latent space. So the main problem in this project is to identify the shared embedding space. So for that, we use self-supervised learning techniques. So that concludes the applications part. Now, a few future directions. So the potential for using similarity learning is immense, but I wanted to highlight a specific focus. See, today morning in the inaugural meeting, there was a topic raised about sustainability, E, right? Earth. We want the future to be sustainable. So United Nations came up with these 17 sustainable development goals. So applying data science to these goals is bound to accelerate the progress towards their achievement, right? So, so in fact, that is one of the components of my course that I teach in US, in San Jose State University, to talk about sustainable applications of machine learning. I'll also take this opportunity to talk about, like I mentioned in the morning, conferences are not just about learning, they're also about networking and finding opportunities and things like that, right? So this is one opportunity. There's a call for papers for this special issue that I'm running. The topic of the special issue is Applied Data Science for Social Good. So if you are working on research projects in this area, social good, please consider contributing to papers to that. Okay, and now for some future technical directions, I just wanted to conclude by discussing these three major trends in this space. First is what is called as deep symbolic regression for recurrent sequences, and the second significant direction is liquid AI, what is come to be known as liquid artificial intelligence. It is based on the concept of a neural network solving a differential equation, neural ODE. ODE, you all know, stands for ordinary differential equation, right? So that is the concept of liquid AI. And the third direction I wanted to quickly talk about is mapping data to function spaces. So given a table, you can always map that table to vector space, right? Each row is a vector, feature vector. So you can map the table to a vector space very easily. But the trend these days is to map to a function space. So there's significant advantages of doing that. I'll give a very brief overview because I think I'm running out of time. First is the deep symbolic regression. I'll explain deep symbolic regression using a, I hope I can share the screen. Let me try. Let me try. I hope this works. Okay, it is. Oh, what it is. Anyway, it's not covering the screen, so I'll just exit. Okay, that's okay. It's not showing up correctly, but that's what I wanted to show is, suppose you give a list of numbers. Deep symbolic regression, what it does is, it generates an equation. For instance, Fibonacci numbers. We all know Fibonacci numbers, right? The sum of the last two numbers is the next number, right? So there's a mathematical expression to generate Fibonacci numbers. Same thing with deep symbolic regression. Given any sequence of numbers, in this case, I tried to give, I wanted to give prime numbers. You know, there is no rigorous mathematical expression to generate prime numbers. But this deep symbolic regression is able to generate an approximate mathematical expression for that sequence. So that's an interesting and important trend. Why? Because you will be able to explain your data using math. So explainability is a very important concept in artificial intelligence, right? See, artificial intelligence today is being used for, in US particularly, it is being used for denying bail or granting bail, you know, criminal cases, right? So for granting bail, they're not depending on judge alone. They're depending on artificial intelligence to make that prediction. Now, if there's no explanation as to why the person was denied bail, it's a serious problem, right? So explainability is a very important concept in upcoming concept in artificial intelligence. So this deep symbolic regression helps in that respect. So there are two approaches to this. One is the famous transformer approach. When transformers these days are ubiquitous in deep learning. So that is one approach. The other approach is using reinforcement learning. Now for the liquid AI part, right? So the liquid AI is based on a very simple concept. The concept is that in artificial neural networks, there are a bunch of hidden layers, right? All the processing happens in the hidden layers, right? So you give a bunch of numbers. It could be pixel values, it could be frequencies, it could be MFCCs, whatever it is. These neurons or these are hidden layers beat up those numbers to generate any kind of numbers that you desire. So that is the idea of artificial neural networks. Now, today morning, I think the previous keynote, the speaker talked about ResNet, right? So ResNet brought up this idea of generating the new hidden state from the previous hidden state, right? So ResNet uses this formula for computing the next hidden state. Now, if you recognize this, if you look at this equation, it is basically Euler's way of solving a differential equation, right? Euler's method. So it essentially solves an ODE. The ODE is given by this. So these arrows are basically tangents. They are like, what is a tangent? It's essentially a derivative. Slope is basically a derivative, right? So if you look at a curve, any curve which models data, in this case this black curve, it is made of these tiny, tiny, tiny tangents. If you, the more the number of tangents, the more continuous the curve will look. If it is discrete, then the curve would be approximated by these tangents, which are not very continuous. But if you reduce or increase the number of tangents, it will become continuous. So that is the idea behind liquid artificial intelligence. So you view this whole series of hidden layers as trying to solve the ordinary differential equation, right? When you note that, what happens is this becomes continuous. ResNet made it discontinuous. ht plus 1 is equal to ht plus some function. So t plus 1, which is this, is equal to where it started plus some function. But in continuous time neural networks, the whole thing is continuous. It basically solves a ordinary differential equation. So this has a lot of advantages. First thing is there's no need for billions of parameters. We talked about ChatGPT in the morning, right? GPT has 175 billion parameters. So each of these arrows is associated with a parameter. So in GPT, there are 175 billion arrows. 175 billion parameters have to be available, which is a very expensive process. Takes billions of dollars, which is not possible for many. But with neural ODE, that disadvantage is overcome. And a few more changes to the concept of neural ODE will bring you to what is known as liquid neural networks or liquid artificial intelligence. This is a paper from Massachusetts Institute of Technology, MIT. So they introduced this concept. And the last topic I wanted to cover is mapping data to function spaces, right? Instead of to vector spaces, we map it to function spaces. What is the idea behind a vector space? There are basis vectors which are perpendicular to each other, right? You all know that. Basis vectors which are perpendicular to each other. Function space has a similar idea. The idea is that the functions are orthogonal to each other. They're perpendicular to each other, right? You map data not to vector spaces, but to function spaces. So some leading questions, right? So what is the abstraction for something that can take a finite number of values? It's a vector, right? What is the abstraction for something that can take an infinite number of values? It's a variable. Variable can take infinite number of values. And what is it that can take infinite number of values that obey certain properties? It's a function. So you can think of functions as a infinite dimensional vector, right? So instead of discrete values, we have continuous values, infinite number of them. So that is the third interpretation of vectors. What are the two interpretations of vectors that you already know? Vector is a point in space with magnitude and direction. And the second interpretation is vector is a series of numbers. Now the third interpretation is vector is a function with infinite dimensions. Or rather, function is a vector with an infinite dimension. So you can view vectors as functions as well. So another example is, so if you plot the bar chart of a vector with 6 dimensions, it would look like this. If it has 17 dimensions, it would look like this. If it has infinite dimensions, then there won't be any space between these bars. It will be continuous. So the vectors can be viewed as infinite dimensional, and functions can be viewed as infinite dimensional vectors. So the same concept that you have in vector space apply to function space also. Only difference is that these function spaces are continuous. So sigma is to sum up discrete values. Integral function is to sum up continuous values. Similarly, norm, orthogonality. The similar concepts exist for function spaces also. Now, an interesting function space is that of a Legendre memory unit. So Legendre memory unit, basically, I mean, there are several function spaces. One of them, which we talked earlier, is a Fourier function space. The second is Legendre. There are several others, there's a few others, 8 popularly. The idea of the function space is that the product of two functions is 0. The inner product of two functions. So of particular interest is the Legendre function space, which is basically a series of polynomials obtained by solving this differential equation. So these polynomials are all orthogonal. To multiply two functions across the time, across their range, you get 0. The product will be 0. So you map the data to these function spaces. There are several advantages to it. See, LSTM works for only at most 1024 or 2048 time steps. But when you map it to Legendre polynomials, you can go back to 150,000 or even more time steps. So that is the advantage. There are other advantages also. You can read up the papers. I think I kind of ran out of time. So thank you all for your attention. And please feel free to collaborate with me.
Any questions?
Yes.
Do you have time for questions? Okay,
Any questions from audience? From online also.
Do you know where San Jose State University exists? California. You want to go there? But why don't you ask sir whether there is any opportunity to do internship during summer break or winter break? You don't want to go there?
They are shy. By the way, majority of my students are from India. In the program that we have from data science program, majority of the students are from India, and particularly from Hyderabad, different institutions in Hyderabad. Okay, there's a question.
The symbolic regression
Right.
can be done by using genetic programming.
Yes.
So what is the gain and disadvantages by these two methods? Can you elaborate on that?
Yeah, thanks for that question. That's a great question. So before deep symbolic regression, the deep symbolic regression was essentially accomplished using genetic programming. But the problem with genetic programming is that the search space is too wide. That makes the process very slow, right? That is one reason, one problem. And the other problem is there's a chances of overfitting are high in genetic programming. So those are the two main disadvantages of genetic programming, which are kind of addressed by deep symbolic regression. So these days, wherever the symbolic space and the search space, the state space is large, there's a tendency to apply deep learning. Even for reinforcement learning, when the state space is too big, people are applying deep learning. That's the concept of deep reinforcement learning. So genetic programming also, same thing is happening.
The second question is pertaining to the functional, converting the data to functional.
Yes.
Already in visualization, there is a Andrews visualization system is there. If data visualization,
Right.
Andrews curves and other things are there in the data visualization. So what is your comparison of these things?
So the idea of mapping data to function spaces is not drastically new. For instance, in linear regression, right? Polynomial regression or linear regression, that is pretty much what we do. We map the data to either a straight line or to a polynomial or to some other curve.
No. The multivariate data representation is in visualization.
Right.
In data visualization, one of the subtopics of the data analytics. In data visualization, we can represent a multivariate vector by Andrews curves.
Right.
So what is, I feel what you are speaking is more or less Andrews curves, where actually that is it takes x1, x2, so on xn are the n Fourier coefficients of the Fourier transformation. Like that, it will be done. So the curves are generated in time by taking these as the coefficients in the Andrews curves.
Yeah, it is a similar concept here. Even in regression, that's what I'm saying. In regression, take polynomial regression. The coefficients are basically what are plotted, right? The same applies here. The only difference is that the space is the polynomial space used in this particular research is Legendre polynomial. That's the only difference. But the idea is basically similar. Any other questions? Okay, if there are no other questions, then thank you all. And please feel free to get in touch with me. Like I said, conference is all about networking and opportunities. So feel free to get in touch with me. Thank you all.
So I thank Dr. Vishnu Pendyala Garu for the informative session on the deep learning similarities in the technology, applications, and the future directions. The similarity features which we can identify like from the mathematical background, and which through which we can classify through classification, regression, and time series predictions. Like the insights on these were informative, and especially the examples like how the Netflix classifies the movies and what is the mathematics behind and how we can do. And similarly, how we can recognize the raga from the Indian classical music. Mapping that with mathematics is impressive, sir. And the topic on mapping data with the function spaces is also informative, and has given good idea on how mathematics can be applied for the real-time applications. Thank you so much, sir, behalf of the organizing committee of the conference. Thank you very much, sir. All the way you came from California to VNR. So we want to see many more times at our college. So we want to collaborate with you to do further. Thank you, sir. Thank you very much for your session. And I